right. Thank you, everyone. Thank you for joining. Hopefully, everyone's having a great Tuesday evening. All right, we shall start. So, I am Thiru. I am a data scientist, and I also lead the artificial intelligence division of Rootcode called Rootcode AI. And by the way, before we start the session, if you have any questions, you can scan this QR code now. This QR code will also put it through the presentation in the middle and at the end. So you can post your questions here so that we can discuss it in the Q&A afterwards. All right, so today we'll be talking about large language models in production. This has been the buzz of the town, right? For the past 6 months, nearly all developments in AI have been related to LLMs. And it's an interesting technology in the perspective that we as consumers also get to use it through services like ChatGPT and Bard. But the models are so powerful that they are not only limited for consumer usage, that we can use it on the data of enterprises too. We can use and leverage these models on our own custom data. And today we'll be seeing how we do it at scale at Rootcode AI. All right. So before we go into how foundation models work and how we can leverage these models in a scalable manner, we need to understand some foundations of the concept of LLMs itself. So before LLMs, there was this concept of foundation models, right? And the idea behind foundation models is that we train massive neural network on massive volumes of data from the internet so that these models develop a generalized understanding of the concepts being trained on itself. Now, there are foundation models for vision, there are foundation models for language. It's a general concept. So it started with OpenAI releasing the first version of GPT around 2018. Then we went ahead with, then we had GPT-2 with 1 billion parameters. And fast forward to today, GPT-4, although the parameters aren't disclosed, it's somewhat within the hundreds of billions. So that's where we are now. So what are LLMs? LLMs are foundation models which are language specific, which are trained on trillions of pieces of text from the internet, from the open internet. And these models are known to have a generalized understanding of language. Although we have seen the popularity of LLMs grow over time, they've been around for quite some time. So it started, we've been having models like MTNLG, the FLAN T5 series from Google, and the OpenAI's GPT series since around 2018-ish. So that's what LLMs are. Large language models are trained to capture relationship in language itself and develop a general understanding of language itself by training on a massive data set. And when we train on the internet, the idea here is that we capture different sources of information from the internet and store it into the network's memory. So when you train a model on the internet, it's going to see a lot of things, right? It's going to see from sports commentaries to scientific journals to all research papers ever published to Wikipedia articles to news. So the idea is that we condense all this information into the weights of the neural network so that it can use this prior knowledge, and we can train these models on separate fine-tuned tasks. So these models aren't trained for any specific task. They are trained to develop this generalized understanding, and then we can use these foundation models for use on pre-trained specific tasks. For example, emotion recognition or text extraction and so on. All right, so before again we go into the depth of how LLMs are trained, we have to make a small distinction between LLMs, large language models, and chatbots. So examples of large language models are Claude from Anthropic, GPT-3 from OpenAI, and the Palm 2 from Google. And these are just the models themselves. Chatbots are applications built on top of it. For example, ChatGPT is built on GPT 3.5 and GPT 4, whereas Bard is built on top of the Palm 2 series from Google. So that's the distinction. What we'll be looking at today is the models themselves and not the application built on top of the model. All right, so it's interesting to see how these models are trained, because understanding how these LLMs are trained will enable us to exploit their properties in training, in using them in production use cases. So now this is, for example, GPT's training pipeline. This diagram is directly from Microsoft, so it's a pretty messy, complex diagram. So we'll decode it step by step. In the first stage, which we call the pre-training stage, we simply train a massive neural network to predict mass tokens, right? So we have excerpts from the internet. For example, here we have a paragraph from Shakespeare, and what we ask the model to do is we mask certain parts of the text, and we ask the model to predict what the words are, simple as it is. And we do this across trillions of pieces of text from the internet over a long period of time on a massive neural network. So the model starts learning patterns like we discussed earlier. But at this stage, the model is trained to predict only the next sequence, right? So that's why these first pre-trained models, when training an LLM, is called the base model. The purpose of the base model is to develop that general understanding of the content which it's being trained on. So this model cannot do any specific tasks per se. For example, you cannot have conversations with this model like we do with ChatGPT. The purpose of this model is to develop that foundational layer of knowledge. So it's simply predicting the next word, nothing complex. And we can see that when we initialize the model, what it's generating. So the idea here is we have a text from Shakespeare, and we ask the model to extend the text and write its own version of it. If, for example, we're asking it to basically imagine its own way of how this text could be continued. And the approach we are using here is something called self-supervised learning. Self-supervised learning is a training strategy generally used when we are training on massive volumes of data where we do not have clean data. For example, here we are using data from the open internet, and the open internet is always messy, it's never clean, right? So self-supervised learning is a strategy we use here where we ask the model to predict the next word given a sentence, and then use its own prediction to carry out the predictions on a cyclical manner, so that it can keep on predicting using an autoregressive approach, right? So simply like this, the model predicts the next word, then uses the previous prediction to make the next prediction, and that's basically the training strategy behind most LLMs. And we can see after a few iterations of training, for example, here after around 250 iterations, nothing much, but after 500 iterations, we can see some patterns forming here. It's trying to form words, but not doing its best. But after 5,000 iterations, we can see that the model is performing somewhat better. And this is the GPT series actually, so we all know how powerful the model is, but this is the capability of the base model. Alright, so we have this very powerful model, but it can only predict the next word or extend sequences. It can't do anything more interesting than that. So they have this foundational understanding, but that's not extremely useful for us in most scenarios. So what do? We simply train the model once more to follow instructions, but this time on a smaller, high-quality data set. So this step is called the supervised fine-tuning step. So in the supervised fine-tuning step, we have supervised pairs of prompts and responses. So basically these are question-answer pairs. We have questions about a particular context, and we have the answer. And we ask the model to, so it's basically supervised. Like given the prompt, it should generate the response. And given on how similar the response is to the ground truth response, we will be backpropagating and updating the weights of the network. This is extremely human dependent. We haven't still found a very efficient way to do this without humans. Even OpenAI, they used thousands of data labelers, spending hundreds of hours on each of these documents to generate around 100 million data points to fine-tune the model. So we take the base model and we fine-tune it to follow specific instructions. And there are other steps too, parts of the pipeline such as reward modeling and reinforcement learning. But the purpose of these two extra steps is to make sure that the model doesn't output any toxic content. Large language models, since they are trained on the internet isn't a very fun, fair place. Always there is a lot of toxic content on the internet. And these reinforcement learning based steps incentivizes the model to basically not generate harmful content and to always generate factual content. So we combine all this, we train this after this massive volume of training on open data, we get this. We get a model which can not only crack cool dad jokes, but it can also explain how a neural network learns in one paragraph. But there's nothing extraordinarily fantastic about this, right? All of us have used ChatGPT by now. It's been nearly a year since its release. And ChatGPT answering questions is not something new for us. But interestingly, what it can also do is that it can also answer questions on data that it's not trained on. This is how it works. So here we have an example. I think it's a bit too small, but it's okay. So it basically says John is 22 years old, and his sister Sarah has an 8-year-old gap with him. So when John was 10 years old, Sarah was 2 years old, and when John will be 100 years old, Sarah will be 92. Is Sarah John's elder sister or younger sister? Now, very simple question. We are just asking GPT 3.5 to do a bit of math. But what's interesting here is the model does not have to look into its previous memory of what it has learned from the internet to answer this question. What it has to look at is the previous context given, understand what has been said in that context, and then answer the question. And it does it. It does it to a certain extent. It does it really well. It says, based on the information given, we can determine that Sarah is John's younger sister, and it explains the reasoning for it. But this also means that if we leverage these models carefully and in a good strategic way, we should be able to make it answer questions on data it hasn't seen. How can we do that? So that's where our ideal topic of using LLMs in production comes into play. By the way, another reminder, if you have any questions, please feel free to scan the QR code and drop it by. We'll be having a Q&A session afterwards. All right, cool. So at Rootcode AI, we work across a range of areas, across a range of industries to implement AI solutions, right? So we work with customers from fitness to healthcare to the United Nations to even European governments in implementing their AI solution. And one of our customers from the automobile sector had an interesting problem. So the story is that this is a 160-year-old company, right? They are one of Europe's largest manufacturers of automobile parts. So they have partnerships with companies like Mercedes and Volkswagen. They are a crucial part in the entire automobile supply chain to some extent. They are based in Europe, and so since they are obviously 160 years old, they have done a lot of projects. They have manufactured a lot of parts, and they have troves of data, very high volumes of extremely sensitive data about these projects. And whenever, reminder to join our Discord community, and whenever they start a project, so this is how the flow looks like, right? They plan and organize the project. They construct and deploy the solution. This is where the engineers and designers come into play. The previous step, it's led by production managers, and they implement it and move it to the factory. So it's implementing a single sensor is a massive process which takes a lot of energy. And throughout this process, some of these projects even last 3 to 4 years, right? And throughout this process, they generate a lot of documents. And these documents are extremely sensitive too. So parts of these documents include designs to cars which hasn't even been released. Braking systems that are custom designed for particular automobile vendors. So extreme amounts of documents. And the problem is that whenever they start a new project, whenever a production manager starts a new project, they have to spend weeks or even in some cases months trying to search through projects files or similar project files to find out lessons learned from similar projects, similar design strategies used, cybersecurity strategies used, and so on. And this was obviously not very productive. Whenever they started a project, this was always the loop, where they had to go through these troves of data again and again and again to find similar projects and the similar strategies they used there, the mistakes made in those projects, the lessons learned, and so on. And this was pretty cumbersome. So they came to us and they wanted to build a conversational layer on top of these documents so that they can access these documents and communicate with them in a very human way instead of having to look through these files one by one and search for information. But in a pre-ChatGPT era, we've been working on conversational AI for a long time now. And we have implemented solutions for different industries. Close to home, we have Sparsalon. But in a pre-ChatGPT era, this would have been a massive project, right? Building a contextual conversational AI agent for an enterprise on their own data would have involved a lot of custom model work. Just to manage the context and memory of the conversational AI agent, we would have to have separate caching mechanism setups, deploy these models in a distributed fashions, include our own custom trained models, and use open source language models. It's a massive pipeline. But not anymore with the GPT APIs. So we had to integrate OpenAI's GPT 3.5 series models with this project data so that there is this conversational layer there so that they can talk with their archived documents exactly. So the first option is the most obvious option, right? We simply retrain GPT, the model, on new data. We have the data, we have tons of documents lying around. Why not just go ahead and retrain it? And OpenAI has an API, a straightforward API to do that too. And they promise that it's higher in quality results than prompt design. It provides more ability to train on more examples than something that can fit in a prompt. And we have token savings due to shorter prompts and the request of low latency. So it's possible. But there is certainly a primary disadvantage in doing that, and we've discussed that until now. Any guesses on what it is? We have a massive point of vulnerability here. Any guesses? If we retrain the model, that's basically privacy. So we were talking about extremely sensitive data here, right? And when we look at OpenAI's policies on how they store data, it's still a bit of a gray area, right? They say they do not use the data for model improvement purposes, but we do not know what the term model improvement purposes cover. And we don't want to ever end up in a situation where the data we used to train they used to train our own model ends up in ChatGPT's training pipeline somehow, and one day someone's querying and there's a new design of a Mercedes that hasn't even been released yet. we don't want to be in that situation. Next, it's way more expensive than using the model API, which we will be just looking at. Third, it's not very scalable when there are new documents being added in the future. And they add tens of thousands of pages of content or internal knowledge every year. And we can't be training for each and every one of that, right? It's not feasible. And so this is the pricing scheme. And we can see that the most advanced model, the Da Vinci series, it's around $0.03 per 1,000 tokens for training. That means if we consider one token as one word, that's not the most accurate estimation. Tokens are parts of words, but just for easy back of the envelope calculation, if we take one token as one word, for every 3,000 words used, we'll be paying $3. And we are talking about millions of pages of documents here. Very expensive. And what's even funnier is that even after training, to run inference on these models, it's even more expensive. So for the usage, the pricing starts at $0.12 per 1,000 tokens. So we can't do that. We have to find an alternative here. Plus, it also takes a lot of manual effort to create the data set. So if we go a little bit back, okay, so this is how the training data preparation stage of OpenAI looks like. The API is extremely simple and we're pretty primitive. What you have to supply is the prompt and the completion. And so here we are sitting with hundreds of thousands of documents. Who's going to write the question answer pairs for each of those documents, right? Not possible. So that's a massive disadvantage. So preparing this data set itself, if we are going to do it, is going to be very costly and it's going to take a lot of effort. So we are down to a second option, which is using prompt-based learning. Now this is the in-context learning strategy we saw early on. So what do we have to do here? We have to take the question, the documents, and we have to combine it together and pass it to OpenAI models, so that given the context, the GPT 3.5 series models will be able to answer the questions. So we have an example. This is GPT generated since we can't use actual customer data, but this is a pretty good representation. We have the context of a project update document, pretty structured. There is a project overview section, there is a project update section, there's a progress update section, and a looking ahead section. And we have a question. So it's about ultra velo sports coupe design project, particular design. And the question is simply, what specific advancements have been made in the integration of lightweight materials, right? So we have the question and we have the context. And if we pass in both of these into the OpenAI API, we'll get a decent result. So given the entire context of the previous text and the question, we have a good answer which says, the sports coupe has resulted in the following advancement: enhanced strength while reducing weight, improved power to weight ratio for better performance, increased aerodynamics and efficiency, improved agility and responsiveness to reduce inertia. Still, there are a few problems here. This again generated using ChatGPT. One of the problems we discussed is the model is using its prior knowledge about automobile aerodynamics and physics to answer the question, which may not always be good, because what we want is the project update from this particular document. And it's also, here we are passing the entire document as context. But it works. It's a workable solution, right? Problem somewhat solved. But what if we have multiple documents? We were talking about hundreds of thousands of documents, right? Regarding hundreds of projects. What do we do then? We can't simply do a string.concat and concatenate every document and pass it as context to ChatGPT. Doesn't work that way. And many models have something called a context length. The context length is simply the maximum number of tokens you can input into the model. So different models have different capacities. For the 3.5 series, it's 4,096 tokens. GPT-4 has a much higher 6,000 tokens, 16,384 tokens. But all LLMs have a limit. At least all modern LLMs have a limit. So what do we do? Anything above this input token length, the API is going to reject the request. The data is not going to be processed. So what do? We need a divide and conquer search strategy here. There are several traditional engineering techniques that we can think of, but they would not work much. For example, let's take Elasticsearch, right? Elasticsearch can perfectly function across, perform search across millions of documents. But the problem is Elasticsearch works based on a keyword strategy. Let's say we enter, depending on the keywords on the question, the context documents can be filtered. Context documents are ideally filtered. The process of what we call as context documents is documents which can potentially contain the answer to the question, right? But Elasticsearch wouldn't work here because the question may not contain the exact keywords which are in the context. And Elasticsearch, although it's good for distributed systems, is not a very efficient or effective text-based context search methodology. So we need to develop our own search architecture here. So if we divide this problem into 3 different steps, first, we need an efficient way to extract context related to the question. Since we cannot pass in all documents, obviously, we need an efficient way to extract parts of the documents which we think could contain the answer to the question, and we pass both of these to the LLM. Problem 2, we need an optimal search strategy, very connected to the first problem, whereas the first problem is extracting these contexts. And after we extract this context, we need an efficient way to search through and pick which context are we going to pass to the LLM. Problem 3, very primitive. We need to make sure that the answers should be accurate. Very basic point, but pretty sophisticated when working with probabilistic models like LLMs. Because the problem is, it's somehow going to try and look into its previous memory when answering the question. And that is not something that we want. And looking into the model's previous memory can also cause problems like hallucination, where the model is making up answers instead of extracting them. All right. So overall, in a nutshell, this is how the most efficient architecture looks like. We have documents. We have document slicing module. We look through this step by step. We have a document embedding module, and we perform a search. How does it work? Again, breaking it down, first we do something called document slicing. Document slicing is simply when we have a set of documents, we try to use the structure of the document and split the documents into meaningful parts. So in this case, in our current example, we have, all right, in our current example, we have 3 contexts, so we have 3 sections. We can break that down into 3 different contexts. Now, once we have these 3 different contexts, we do something called an embedding. Now, an embedding is a pretty simple concept. I think if we have people from a computer science or ML background, embedding is one of the foundational concepts of language understanding, but we'll go through it too. So we take these extracts from the document and we pass it through an embedding model. An embedding is basically only a numerical representation of the text. And how does it work? You can imagine, since we are in the space of numbers, since embeddings are the numerical representations, and by the way, we do not use the standard GPT 3.5 models here. There is a separate embedding model in OpenAI where we can pass the text and get the embeddings. And now if we imagine these if we put these documents in a 2D coordinate grid, when we get out the embeddings, context or parts of documents which are similar to each other will align up closer to each other. And what we can then do is we can embed the question also, and we can sort of project it in this embedding space, or just for the simplicity of argument, this two-dimensional space. And we can see which are the contexts which are closest to the question. So let's say for our particular question, not every paragraph contains the answer to it. So we need to filter and extract the paragraphs which are necessary. And we filter out the context closest to the question. And what we do here is, now every time when a user asks a question, we can't go and calculate the embeddings or calculate this numerical representation for all document slices, right? We can't do this. We need a way to sustainably sow and search through this data. And that's where we use vector DBs. That's where the concept of vector DBs comes along. Like any different kind of DB, vector databases similar to relational databases and NoSQL databases, they are specifically designed for the purpose of storing and calculating vectors and making calculations in these vector spaces. So if we go through and review this pipeline once again, we have a user question and we pass it through the OpenAI embedding model. We get the embeddings out, and then we have a vector search module. Now this vector search algorithm, there are different ways to implement it. The most primitive way being calculating the Euclidean distance, that is basically calculating the distance between the closest points and trying to figure out which contexts are closer. But there are more sophisticated strategies to do this too. So we calculate we get the embeddings and we pass it to the vector search module, and we get the extracted context. So now given a question, we have a set of contexts which we think may contain the answer. And then what we do is we combine this context and question, and then we pass it to the LLM. Now there are different strategies in which we can use here too. One strategy is called stuffing. Stuffing is what we have done here, where we get the context, we filter one context which we think is the closest match, feed it along, then pass the question. There are other slightly advanced techniques called MapReduce too, where you try to have when you have multiple contexts, instead of choosing which is closest, you take all three of these contexts, all three of these paragraphs which we think contain the answer, and we pass it with the question 3 different times. So it's 3 different calls to the API. We get 3 different answers, and then we make a 4th call to the API to the model, asking it to grade each of the answers. And whichever answer has the highest grade or has the highest scoring by the model, that particular answer will be picked. But again, there's a problem here where this can be pretty inefficient, because we are making multiple calls to the model, which can quickly become very expensive when we are in a production scenario. So all done. When we pass in the context and the question, the model gives a somewhat good answer. The integration of lightweight materials reduces its overall weight, improves power to weight ratio, and enhances handling and agility. Compared to the previous answer we got, this answer is shorter. It doesn't have a lot of the technical explanation provided by the model. But that is because it's only referring to the context which we gave through the document, and it's not accessing its previous knowledge. So our first problem is solved. We need an efficient way to extract context related to the question. We've done that. Second problem is also solved. We have a somewhat good search strategy now. But the third problem, where the answers should be accurate and should only depend on the context being provided, it's still an open area. Because still the model could go back, look into its prior knowledge of what it has learned from the internet, and curate an answer. That's where the concept of system prompts come in. System prompts are a very simple but powerful concept when working with LLMs. So system prompts are prompts which we attach with every request, where we ask the model, where we instruct the model on how it should behave. So for example, whenever we send a question, we send it with a pretext saying to the model saying, answer the question based on the context below, and if the question cannot be answered using the information provided, answered with I don't know. This is simple, but this is a straightforward way to prevent the model from hallucinating or making up information. Now, again, there are different approaches we can take here too, where instead of the model responding with I don't know, we can create somewhat of an action logic here, where when it detects it doesn't know the answer, we can probably trigger an internet search and get the answer. So going through the pipeline, we have the documents. We slice the documents into sensible context pieces. Then we embed these documents and store them in a vector database. And then we come to the user's questioning part. When a user asks a question, we get the question, we embed the question, and then we pass it to our vector search method, where we load it through the vector DB and try to find the context which make most sense. And we combine them, we generate a prompt out of it, and then we pass it to the LLM. But it's important to take concern of the bias and safety aspect of it, because we are ideally building a system which is going to be used by very powerful stakeholders in an organization to make some serious decisions. So, A, we don't want these systems to provide wrong answers, and B, we don't want their inherent biases to be reflected on their answers too. First problem being hallucination, something we've been talking all along. So this is very natural to GPT-based models and mostly any LLM. All of us have seen memes of where ChatGPT has messed up. So here the question is, what is heavier, kilo of water or kilo of air? It says kilogram of water is heavier than a kilogram of air, but that's factually inaccurate. The masses are the same, so it's the same weight. It's the same mass ideally. Second is the privacy of data. This is extremely simple and straightforward at first, but it's one of the easiest to be mistaken on. For example, in our case, our customer was based in the EU, and all data was supposed to be stored and processed in the European Union. But when we first started working with OpenAI, we realized that in their policy, we do not have much control over where the data is stored. And the moment, let's say without knowing this, we accidentally sent some documents or sent some context from documents to OpenAI, and it's stored in a server somewhere in the US, that's a direct breach of GDPR. And that's not something we want. And on top of these regulations like GDPR, industries have their own specific regulations. For example, in the medical industry, we have HIPAA regulations, and automobile, they have their own regulations on how their data should be processed. So we don't want to have such breaches. And we recently saw that Facebook had nearly $1 billion fine just for moving data in and out of Europe, moving from US servers and so on. So we don't want to do that. Second is opinions versus facts. This not only comes in along by engineering the system, but it's also on instructing the users on how to use conversational knowledge bases or conversational mediums to access organizational knowledge. We need to instruct the users to make sure that they ask for facts from the systems instead of opinions. Instead of asking GPT 3.5 how good two ideas are, this system should be used to get factual information, because the moment we ask its opinion, we are opening up to a series of biases which it can possess. and optimizing for costs and inference time. This is a goal in in devising any architecture. We don't want our customer to see a $20,000 bill at the end of the month, right? That's something we want to avoid. So how do we make sure that when working with LLM-based systems that we reduce costs and inference time? One is we try to compress the embeddings and store them, perform the embedding search and storage optimally so that they don't occupy a lot of compute space or they don't take a lot of time to search. Second, in terms of optimizing for costs, we try to minimize the prompt as much as possible because that's where the billing starts. So that's something we look forward to optimize to, and that when architecting this solution should be one goal to always reduce and optimize on. Now, talking about the tech stack to do all of this, we work with a range of technologies when we build our products, but specifically when working with LLM, we use the LangChain framework to integrate all of this, to connect to the data sources, to connect to the vector DB, and to connect to the model itself. LangChain is one of such frameworks. Hugging Face has some similar features, and Cohere is a proprietary product which is not open source. The other two are open source products. Vector databases, we have FAIS, that's from Facebook AI, and we have Pinecone, which provides native integrations to AWS and GCP, and we have databases like Milvus. Models, we have Claude from Anthropic. Claude is in a closed beta, but GPT-3 and 3.5 are the current top standard models, the cheapest, most efficient models to use. We also have a series called Palm, that's from Google, very recently released, very effective series of models, but extremely expensive, and they are also in a closed beta in Google Cloud too. So, in conclusion, large language models are extremely powerful tools, but only having the language model itself isn't enough to solve problems with them. We need to architect solutions around them and make sure the data strategy is formed around it in such a way that not only we make sure the data is secure, but we also make sure we only exploit or take advantage of the positives of LLMs. Because there are a host of problems with them too, like bias and false information, and we need to build proper firewalls around it to make sure we don't get impacted by it, or our solutions don't get impacted by it. All right, that's it for the session. Thank you everyone for listening.